test coming up tomorrow. Do you remember what we've covered so far in this chapter? Yeah, okay. Chase says, no, I have no idea what I've been doing for the past 2 weeks.
Not really.
I have been on Mars. Okay, so the first section in this chapter was permutations and combinations. Right, we spent like 2, maybe 3 days on that. Alright, what's the difference between a permutation and a combination?
Permutation.
Order matters on permutation.
Someone give me an example of a permutation, some kind of situation.
First, second, and third.
First, second, or third, out of what? What are we picking?
A race.
Okay, we have a race, how many people are competing?
12.
We have 6 people in this race. We want to know how many ways we can get first, second, or third place. How many ways we can award first, second, and third place medals. That is indeed a permutation. Very good, Vinny. All right? So, it's a permutation. Order matters because if we give someone first place, second place, or third place, it's a lot different than if we kind of switched them around and gave them the medals again. Right? So, if I were to take that scenario, we have 6 people in a race, I want to know how many ways I can award first, second, or third. If I were to take that permutation and change it and say, okay, I have 6 people in a race, I want to know how many groups I can have, how many groups of 3 people that can be on the podium for first, second, and third. Right? So now this is a combination, right? The order doesn't matter. I just want to know how many different groups of 3 people I can stick on the podium. Doesn't matter what order I choose them in, doesn't matter what order I'm putting them on the podium. Just these different groups of 3. Does the difference there make sense? Yeah? Do we know how to get to those things on your calculator?
I suppose.
Yes, we do.
Math.
Probability. And PR and CR. What value comes first?
The smaller. Value bigger.
The bigger value, the total number of things you're choosing from. So in this case, 7 racers, right, or 6 racers, that's going to come first. We have 6 total people, and we're going to choose a group of 3 of them, right? 6, choose 3. Bigger number comes first. You can have a smaller number come first in a case like that. I won't let you. All right? Are we good on that? All right. The next thing we talked about was theoretical versus experimental probability. What's the difference? What's theoretical probability?
Where I don't really know what it's based on, but like if you flip a quarter, there's 100% chance that it has and 50% chance that it fails.
Exactly. So in a perfect world, this is what should happen. This is the probability that this event should happen. If I flip a quarter, there is a 50% chance that it will land on heads. If I draw a card, there's a 50% chance that it'll be red, right? So that's the theoretical probability. Theoretically, in a perfect world, this is the probability that such an event should happen. What about experimental probability? How is that different? Exactly. It's what really happens. So if we actually flipped a coin, right, we kept flipping and we kept flipping, our total number of heads over our total number of coin flips will give us our experimental probability of flipping heads, right? And it might not be the same. We worked with this a little bit, and it's the more flips that you do, the closer it gets to the theoretical probability, but it might not ever actually be the same. Okay? We also talked about geometric probability a little bit in there. Right, there were like a problem or 2 on that. Right, who remembers what we did next? It involved the word and. And. Independent or dependent events. So if I had, let's see, I'm rolling a dice. And I want to know the probability of rolling a 2 and rolling a 3. I have 2 dice rolls. Roll a dice, I'm going to roll it twice. The probability of rolling a 2 and the probability of rolling a 3. Is it independent or dependent? It's independent. Why? Exactly. My first roll doesn't affect my second. If I roll a 2 on the first roll, it's not like the face that has a 4 completely disappears from the dice. Right? It's still there. It doesn't affect it. Just like if I'm picking marbles out of a bag, and I put the marble back after I picked it, that would make it independent, right? Because your first choice really has no effect on your second. In dependent events, it's a little different. So in dependent events, I'm picking marbles out of a bag, and I'm not putting them back. You know, stuff them in my pocket, or set them on the table, or throw them across the room. Doesn't matter what I'm doing with them, as long as they're not going back in the bag. All right, so this changes the probability for your second or your third or your fourth event, right? Because you're having less and less marbles to choose from. How do we calculate the probability of an independent event? You remember? And, big flashing roadside, multiply. So for an independent event, you take the probability of your 2 or more events. So the probability of choosing a 4 out of a deck of cards and choosing a 5 out of a deck of cards. We're going to multiply them together. For dependent events, it's similar, but a little different. So we multiply them, but our second probability has to be after the first has already happened, right? So if we choose 1 marble out of a bag of 10, right? So we're going to write the probability of that first event, grabbing a red marble out of a bag of 10 marbles. Well, now for our second event, we didn't put that marble back. So now we're no longer choosing out of 10 marbles, we're choosing out of 9. Right? And that's what it means when it says after the first has already happened.